All right, guys, we're going to talk about conservation of momentum. So in class, we started to talk about momentum. Momentum is the mass of the motion of mass. So when we're talking about conservation of momentum, we're talking about the idea that momentum in the system is not created or destroyed. So this is the idea that my initial momentum is going to be equal to my final momentum. This is like the main equation for this. We could also expand this out to say m1v1 plus m2v2 equals m1v1 plus m2v2. This whole side would be my initial, this whole side would be my final. Now this only works in an isolated system. So the isolated system includes the collision between the objects and the force between the objects. There's no external forces. So we're not going to talk about air resistance. We're not going to talk about friction. If you have questions about this, you're welcome to. I included a link to the physics classroom so you can write through this. So I have a couple problems we're going to look at. This first one, a 4,800 kilogram truck traveling with a velocity of positive 4 meters per second collides heads-on with a 1,200 kilogram car traveling with a velocity of negative 12 meters per second. The truck and the car entangle and move together after the collision. So the first thing you should ask yourself is, what type of collision is this? So this is an inelastic collision. So when the collision happens, two objects stick together. This is the sticky collision. So we want to determine the velocity of the truck and car immediately after the collision. So we need to keep in mind that momentum initial is equal to momentum final. And I'm going to sub in my equation. m1v1 plus m2v2 equals, now since they stick together, I can just say m1 plus m2 times v. So let's plug in our knowns. 4,800 times 4 plus 1,200 times negative 12 equals, and 4,800, well, not 48, 4,800 plus 1,200 times velocity. All right, so this gives me 19,200 minus 14,400, which equals 6,000 when our masses are added together, velocity final. So these two subtracted from each other gives me 4,800 equals 6,000 V. So my velocity final is going to be 0.8 meters per second. Now we want to determine the truck's momentum change. So the truck's momentum, change in momentum, would be the momentum final minus my momentum initial. So my mass stays the same. So we're going to say that this would be delta P equals mvf minus mvi, which gives me 4,800 times 0.8 minus 4,800 times 4. This gives me a total change of momentum for the truck of 15,360 kilograms meters per second. So now let's look at the car's change in momentum. Again, the same problem. Change in momentum equals momentum final minus momentum initial, which gives me mass times velocity final minus mass times velocity initial. So 1,200 times 0.8 minus 1,200 times negative 12, because our car was moving in the negative direction to begin with. This gives me, when I multiply those and add them together, 15,360 kilogram meters per second. So the cool thing about this is my total change in momentum between both vehicles, since these are the same but just different directions, my change in momentum total for the entire system is 0. All right, let's look at another example. An astronaut is floating in space near her shuttle when she realizes that the cord she's supposed to attach to her ship has become disconnected. Her total mass, bodysuit, and equipment is 90 kilograms. She reaches into her pocket and finds a 1 kilogram tool and throws it into space with a velocity of 3 meters per second directly away from the ship. So guys, we've seen this problem before when we were talking about Newton's third law. If the ship is 10 meters away, how long will it take her to reach her ship? So let's draw, here's my lovely spaceship. Oh, isn't it beautiful? Lovely spaceship. Here's my person out in space. Oh no. And she has her tool. Her tool is going 3 meters per second that way. Now we know due to Newton's third law, if she applies a force to the tool applies a force to her, which is going to cause her to go with some sort of velocity. Now, if we can talk about explosion, we know that M1 V1 plus M2 V2 equals M1 V1 plus M2 V2. This is just our conservation of momentum equation. However, if the velocity is 0 at the beginning for both of this gives me 0 momentum equals mass 1. So if she throws a 1 kilogram tool, we have 1 kilogram times our velocity. I'm going to say it's -3 because it's moving to the left, plus our no mass. Now, if she had 90 total kilograms and she threw 1, her mass going to the right is 89 kilograms. 89 times V2. So I need to add my velocity, my 3 to the other side, which gives me a velocity of 0.034 meters per second. Now, that's not what my question was. My question was, if the ship's 10 meters away, how long will it take her to reach it? But this just gave me my velocity. Now, if we're in space, there's no acceleration. So we can treat this as a constant motion of problem, where delta x is 10 meters, velocity is 0.034 meters per second, and time is what we're solving for. So delta x equals v times t. 10 equals 0.034 times t, which gives me a time of 296.7 seconds. So this is a good problem because it asks us to apply what we know about forces, momentum, and kinematics all to the same situation.